2013, FRQ number 2. I'm not going to read through the problem. You guys all know what it said. Number 1 just wanted a free body diagram. So, you had the applied force pulling forward. The problem described drag force, so you had to identify drag force. Just because it helps me process stuff, always like to write down the magnitude of the forces, so maybe without the negative. Yesterday we talked about the fact that you should put in your force of gravity as mg, and then there's got to be a normal force. I wrote myself a little note that it was equal to mg. I think technically for full credit, all he needed was the labels. Cool? Any problems with A? All right, B. Part B says, write but do not solve a differential equation that can be used to determine the speed v of the box as a function of time t. If you need to draw anything other than what you've drawn in part A to assist your solution, use the space below. Don't add anything to the figure name. Also, incidentally, on the real test, these will be obviously spread out more, right? Like, hopefully that's obvious. All right, so this was part A. Part B. So we're trying to find an expression for the velocity at time t. So, sure.
Wait, I was just going to ask, would we even mark down if we did or didn't have that negative on the kV?
No, I don't even think you needed the kV at all. I think if you just wrote FD, you were fine.
Okay.
Cool. All right. So part B, we're trying to find the velocity as a function of time. So it's about forces, right? So let's start with our standard net force equals net force, right? Okay. So our net force is the mass of the box times the acceleration. In terms of sums of forces, that's going to be my applied force minus my drag force, which I'm going to write as kV. Cool? Everybody good up to there? All right, so we've done a bunch of these now. What's the next step? Acceleration is dv dt, so this becomes m dv dt equals applied force minus drag force. Everybody good up to there? I think technically you can stop there. That's a differential equation that you could use to solve for the velocity as a function of time. Cool? Now, I don't know why they put C where they did. D wants us to solve it, so we're going to come back to this in a minute. So really quickly, let's do a quick side note and do part D. D wants to know, and remember, it says to solve in terms of the given variables. Okay? Come up with an equation for the terminal velocity. So, do you guys understand that this applied force is going to cause the mass to accelerate? Right? But since my drag force is equal to kV, as it goes faster, the drag force is going to get bigger, right? Describe, what does terminal velocity mean? Sure, we got here.
It's when the drag force is equal to the force of gravity of the force.
Yeah, it's when your drag force cancels out the force that's producing the acceleration, right? In other words, when your net force is 0. So for part D, we want to figure out at what point our net force is 0. In other words, we want to figure out when our drag force is equal to our applied force, right? So all you had to do there was just go, oh, well, the drag force is, don't even worry about the signs, right? We want the magnitudes to be equal. So we need kV equal to,
That's part C.
oh, dang it. Thank you. This was part C. Sorry. Thank you. Equal to our applied force. When that's true, we will have reached our terminal velocity, right? So, terminal velocity is just the applied force divided by k. Done. Follow? All right, so now let's go back to part D. So part D wants us to solve this mess and come up with an expression for the velocity as a function of time. So really quickly, and I wish I had checked this before let me see. What is this? This is question 2D. Oh, wow, it is a lot of points. Ugh. Wow, that's 5 points. All right, never mind. I was going to say, all right. Okay, so now we got to solve this for part D, right? So, first step, Help out, you guys. What's the first step here, you guys? Separate your variables, right? Get all of the v's on one side and the t's, if there were any, on the other side, right? So I'm going to divide both sides by this mess and multiply by this. So you get m dv over applied force minus kv equals dt. You guys agree that that is the same as this? Okay, so now to solve it, we got to integrate this mess, right? So when I integrated, I pulled the m out. So my next line looks like this. M times the integral of dv, of fa minus kv equals the integral of dt. And now we need to set our bounds of integration. So I want to find the velocity at time t. So my time is going to start at time 0 and go up to time t. What does the velocity begin at here, you guys? 0. Tells you that the box begins at rest. And it ends at the velocity at time t, right? Everybody good up to there? All right. This is, what we're about to do is as hard as the integrals will ever get. Okay? And if it's anything other than power rule, or maybe occasionally a simple trig thing, it'll be this. All right? So this one is tough because the v is on the bottom, but there's no exponent. Okay? So anytime the variable that you're integrating with respect to is on the bottom of a fraction with an exponent of 1, it's a natural log. Okay? So this integral is going to be in some fashion the natural log of this. Okay? So remember, the derivative of a natural log is 1 over the thing, right? But then chain rule, we would end up multiplying by negative k, right? So I need to have over negative k, right? That's a little sloppy. We'll move the negatives around, but that's the deal. Follow? And then don't forget to bring down your mass. Do you guys agree now that the derivative of this mess will give us what we started with? Everybody good? Molly, you good? You're making kind of a, what else did we just do face? Talk to me. The k. So remember, when you take an integral, what you're really asking yourself is, the derivative of what will give me this thing? Okay? So because this is 1 over, I know it's going to be a natural log. Okay? So now I want to set this up. So whatever this mess is, when I take the derivative of it, I have to get that. Okay? So if I just take the derivative of this, I'm going to get 1 over fa minus kv. But then the chain rule says you also have to take the derivative of what's inside. So the derivative of what's inside is negative k, right? But there's no negative k up here, so it must have somehow been divided out. You see what I mean? So now when you take the derivative, you're going to multiply by negative k, and they'll cancel out, and you'll get what we started with. Does that make backwards? Or does that make sense? I was going to say, never mind, that's not what I was thinking. Does that make sense? Does that make backwards, is what I just said. All right. All right. All right, so any problems there? All right, so don't forget to bring down the m. Then we're evaluating between 0 and v of t. What does this side of the integral give us, you guys? Just t, right? Good? Any problems before I go on? All right, now, integrating this mess is kind of a, well, it's a mess. So here is, I think, what I'm going to do. Let's do this. I'm going to move the over negative k to be like this, negative k, and then just do one of these. Does that make sense? All right, so this side of the expression is going to be negative m over k times, let's see, I got to plug in my values. The natural log of force applied minus k v at time t. So that's the top one, right? Now you got to be careful. Just because this is 0 doesn't mean I get 0 when I plug it in, right? So you actually have to plug 0 in for v and see what you get. So you're going to get the natural log of FA, right? So minus the natural log of FA. Equals t. Yeah, Sebo.
Does that mean that we should write on the bottom of that evaluation bar v of 0?
V of 0 is 0. The problem tells you that at time 0 your velocity is 0. It tells you it begins at rest. If it didn't, then you're right. Then you would want it, instead of having 0, you'd call it v naught. Good?
Yep.
And that would suck. That would be like an extra layer of grossness. All right, everybody good up to there? All right. I feel like there should be a way I can simplify this giant mess here. I've got a natural log minus a natural log.
Yes, you can divide that.
Yeah, you can rewrite that. There's a name for the rule. That the natural log minus a natural log is the same as the natural log of the quotient, right? So now I've got negative m over k times the natural log of applied force minus k v of t over fa equals t. We are now through the worst of it, so let me pause there for a minute. Have I lost anybody? All right, so the original problem wanted us to solve for v of t. So now we got to find a way to get this v of t by itself. So let's start by moving the m over k. So you get the natural log of fa minus k v of t over fa. Oops, I have a weird parenthesis there for no reason. My eraser is too big. I need to fix that. Equals negative kt over m, right? Everybody good? Is anybody ungood? All right. How do I get rid of this stupid natural log? You take both sides and raise e to that power. Cool? Because e to the natural log of something is just the something. So now I've got applied force minus k v of t over applied force equals e to the negative kt over m. And from this point forward, it's just basic algebra, right? Multiply by fa, subtract out fa, and then divide by k, negative k, I guess. I'm sorry?
Did we want it to equal v of t?
Yes.
Okay.
Yeah, so you're solving for v of t.
It's like a math test.
What's that?
It's like a math test.
It's
like,
I know, and that's 100% math. That's this part of it is more math than physics, which sucks, and I don't know why they put such an emphasis on it, but it's a thing.
do you need to solve for VT?
Yeah, yeah, and I think if you look at the way it's, well, let me see. You do? Okay. I'm still learning the scoring guidelines myself.
You get a point for attempting to solve.
Okay.
That's probably
And then another
because
point
no
for-
one
yeah.
successfully does it.
Yeah, so I don't know if you guys noticed that. Josh just pointed out that once you get it to, it looks like, after you complete your integral, basically, you get a point for trying to solve for VT, and then another point for doing it correctly. Okay? So,
Could you
that's...
just say VT equals and have no idea what you're supposed to do to actually get it, but since you try to get that point?
I don't know. I think it needs to be a legitimate try. That's going to be a judgment call by the graders. Yeah. Yeah, totally. Okay, everybody good up to here?
Yep.
Do I need to finish, or are we good from there? All right, everybody's happy? All right, so that was number 2. Any questions? All right, so on the positive side, as far as calculus goes, that is absolutely 100%, I guarantee you, the hardest it will get. Okay? Cool?
Cool.
All right, nextest. I don't know why I said that way. Let's see, number 1. FRQ number 1. So this was the one that had the experimental data, right?
Yeah.
Yeah, with the spring and stuff. All right. So the first thing you had to do is you had to plot the data, right? Important things to notice. Here are some things that you are told that you have to know. The little glider thing begins at rest at a position of 0.25, and then you push it back to a position of 0, which means that your displacement is 0.25 meters, right? I guess technically negative, but whatever. All right? So when you're thinking about your elastic potential energy, that's the energy, or that's the, the displacement that it undergoes. Okay? So then it's held at rest, and you release it from a position of 0, and then it gives you this velocity as a function of time chart. Good? All right. So when you plot the velocity time graph, here's what the things that you need to make sure that you ensure. All right. So if you plot the data, you get, and I'm going to kind of fudge this because it's, you guys can plot data. So you're going to get a point here, and then you get a point here-ish, and then you get a point. Oh, let me make that a little higher up. You get a point here-ish, and then a point here-ish, and then one here, and then you get one that's like here, and here, and here. All right. If you read through the text, the problem tells you that the glider leaves contact with the spring after 0.79 seconds. Why is that important? It's going to stop accelerating after that point, right? So what should the velocity time graph look like after that?
Line.
What kind of line? Every line is straight. Be more specific. A horizontal line. So your graph should be curved and then basically straight from that point on.
Okay, so one of my biggest questions about this graph was how, do you know, what the asymptote is?
Well, I mean, just by, if you plot the points, and are you on the same problem as us? This is number 1A?
Oh, never mind. Wait, no, I got that one. We're good.
Okay, yeah, there's another one where the asymptote's a little trickier, and I'll talk about that in a minute.
Okay.
Oh wait, did I skip a thing?
So you're one.
Oh, I skipped part E on the last problem.
Oh,
And that's what you were asking about.
Oh, oh,
because it kind of looked the same. I'm sorry.
No, I get it. Shoot. Let me jump back and get that before I get too much farther into this. I'm sorry. It's totally my bad. All right. So jumping back really quickly to problem number 2. I apologize. It wants the graph. So, do you guys agree that the velocity is going to increase under that applied force, but at a decreasing rate as your drag force gets bigger, right? Read question C. Determine the magnitude of the terminal velocity.
Oh, you just use that,
That's your asymptote.
so you don't have to find the number.
I honestly didn't look that carefully at the grading sheet. My assumption is that you would have to label VT equals FA over K, which is our answer to C. That should be your asymptote, and then your velocity increases with that as an
But
asymptote.
you don't need it as a number.
Correct.
That's right.
Does that make sense? All right, cool. Thank you. I apologize for skipping that problem. Everybody good then with that? All right, right on, cool. All right, so back to number 1. All right, so is everybody good with this graph? Okay, part B. The student wishes to use the data to plot position X as a function of time t for the glider. Roman number 1, describe a method the student could use to do this. Well, look, you guys, this is a velocity of time graph. So what do I have to do to this graph to plot position as a function of time? Integrate. So the student should plot the area under the curve as a function of time. So you can count boxes and find the area under the curve after 0.1 seconds, after 0.2 seconds, after 0.3 seconds, etc. Cool? And if you look at the grading scale, it literally just says plot the area under the curve as a function of time. Cool?
very
Roman numeral 2. On the axes below, sketch the position, sketch this graph. All right, well look. How do I want to say this? So right now we're trying to plot a position time graph, right? So for part of our motion, the velocity is constant, right? Show me with your hands, you guys, what should the velocity time graph look like for this portion here where the velocity is constant?
Position time?
You said velocity.
Sorry, what should the position time graph look like? It should look like a straight line, right? So this part here needs to be a straight line, right?
All lines
Good.
are straight.
Damn it, you're right, my bad. You're right, I'm an asshole. You're right. It should be a slanted line. Good? What are you doing, Teddy? You good?
No, I was just doing what Carlos said.
I was doing this. I don't know what you're talking about.
All right, is everybody good? All right, now, what is this part going to look like? It's got a curve, right? As your velocity increases, your graph has to get steeper. Cool? So that means that my graph should look like this. It should get curved and then a straight line, right? That's 2 of 3 points. I did something terribly wrong. Seba, what do you got?
I thought that the curvature of this x of t should be the other way around.
Oh, for this, you thought it should be this way?
Yeah.
Is the slope of this line increasing or is the slope of the line decreasing? Oh, no, don't listen to me. Don't think about it that way. Sorry, that's acceleration. The velocity is increasing, right? Do you agree that the velocity is increasing? Even though it's getting less steep, the velocity is increasing, so it's got to get steeper. So it's not this, it's this. Okay? But there is another issue with my graph. I don't know, Anthony, what do you got?
Like you can't have like the kind of corner things as you differentiables.
Very good, yes. So the idea is, remember, the slope of this curve represents the velocity at that instant. So the way I have it drawn, I'm showing it going super fast and then suddenly slowing down, right? It needs to be a smooth transition from the curve to the line. Follow? So, oh, cool. Try that again. So, it should look something like that. Okay? And although I didn't do a great job of showing it, what should that time be? 0.79 seconds, right? And I believe in my quick skimming of the scoring guidelines, those were the 3 things they were looking for. They were looking for this being curved, this being straight, this being a smooth transition. I guess this is 4 things. And then the time there being 0.79 seconds. Cool? Any questions? All right, how we doing? Let's see. Part C, calculate the time at which the glider makes contact with the bumper at the far right. So this, I think this of the problems, this was probably the most straightforward. How far does the glider have to go before it hits the bumper? After leaving the spring, how far does it have to go? 1.75 meters, right? And it's going at 5 meters a second, so you can find the time for that, right? Plus the 0.79 seconds it took to leave the spring, and you're done. Now, also acceptable was finding the area under the first 0.79 seconds. Did you try to do something like that? To figure out how far it traveled before leaving?
I didn't really do it exactly for the velocity graph to find the change in position.
I got trying. So if you came up with somewhere, and look at the grading sheet, it'll tell you. There are a couple different ways of doing it. All right, everybody good with that? Okay, part D, calculate the force constant of the spring. So I know that the velocity of the cart goes from 0 to 5 in 0.79 seconds, right? Or 0 to 0.5? can I just find the acceleration and then do mass times acceleration?
No, because force is not.
Good. The force is not constant. So you should not be using F equals ma anywhere in part D. If you did, that's wrong. Okay? Anybody find a way around it? Yeah, we got Jacob. Yeah, conservation of energy, right? So the idea is the elastic potential energy when it's squished is equal to the kinetic energy when it leaves. So you get 1/2 k times 0.25 squared equals 1/2 the mass, which I think was 0.4 times the velocity squared. And solve for k and get 1.6 newtons per meter. Yes, sir.
Kind of noticed on a lot of the story rubrics or whatever that like sometimes they word points for saying that E equals KD before putting all the numbers in. I tend to go straight to the numbers, so I have to make it habit of it.
I would, yeah. And that's a thing I need to be better about next year, is stressing that stuff along the way. Yeah. So, but I mean, think about, like, put yourself in the shoes of the grader, right? Like, they want to be able to look at your paper and know what your train of thought is. You know what I mean? And, yeah, you know what I mean? And, like, so, yeah, you should get in the habit of writing stuff out in symbols, then numbers. Symbols, then equations, then numbers.
I don't have much time to get to that habit now.
Yeah, I know. I hear you. I'm sorry. All right, cool? Do your best. People last year were fine, and I made the same mistake last year. So. All right, everybody good? All right, finally, part 3. The experiment is run again, but this time the glider is attached to the spring rather than simply being pushed. Part 1, determine the amplitude of the periodic motion. 0.25 meters, right? It tells you that in the problem.
Yeah.
Cool? Determine the period. There are 2 ways you can determine the period. You went into the super secret ninja route?
Yeah.
How long does it take for the cart to go from compressed to the midpoint where it leaves the spring? 1/4 of the period. So 0.79 seconds times 4. There's your answer. Or, the way that I did it, the harder way, is to do period is 2 pi root m over k. You know your mass. You just found your k.
I don't have the equation sheet, so I have to remember if it was a K over M or M.
Gotcha.
So I
Keep
got
those equation sheets handy while you're taking the test so you become familiar with it. Okay? All right, everybody good? All right, last.
I also forgot that the rotation order.
Yeah. We do. It's a little, I'll explain in a minute. You do. It's one more FRQ, but one of the problems, I was trying to remember, I felt like I gave it to you. I think it may have been on your midterm. So one of the problems you've already done. But I'm guessing, yeah, it is what it is. All right. Okay, so here's what we've got. For number 3, you've got a rope attached to the ceiling. It goes around a disc, and then you pull up over here with a force that is called FA, as in applied force. The problem tells you that this thing has a mass of 2 kilograms, so I'm going to go ahead and find my force of gravity. For simplicity, I'm going to use 10 for the acceleration of gravity. Is that going to mess anybody up?
No.
So 2 times 10 is 20 newtons, right? All right, you're told the radius of the disk. Let's make a quick note of that. It's 0.1 meters. The rotational inertia of a disk is mr squared over 2, or 1/2 mr squared. All right. A says calculate the magnitude of the force FA necessary to hold the disk at rest. Well, if it's at rest, we need our net force to be 0, right? So 10 newtons here, 10 newtons here would do it, right? So that's it, 10 newtons. Good? All right, now, part B. Part B is tough. As long as there is no acceleration here, these 2 tension forces are going to be equal. Okay? As soon as there is acceleration, so in the problem it makes this 12 newtons, right? Which is more than the 10 newtons you need to keep it at rest, right? So do you guys agree that's going to make the disk turn this way? Doesn't that mean that this tension force over here has to be less than 12? right? Because otherwise it wouldn't turn. How much is it? I don't know. But it's not 12. It's got to be less than 12. So let me pause there for a minute. Does that make sense? All right, now, if the disc was frictionless, so that it just slid up, then you'd be good, and this would be an easy problem. Okay, but because that disc is rotating, it gets complicated. All right, so what two big sort of systems of equations or concepts should we be thinking about here? Torque and net force. So I'm going to set up, so the question wants to know, during this situation here, this is part B, right? Calculate the linear acceleration of the disk. So I'm going to set up two equations. Net force equals net force, net torque equals net torque. Follow? Cool. So, net force equals net force. So that means that my tension force plus 12 newtons minus 20 newtons has got to equal MA, right? Oh, we know what M is, right? Follow? Simplify this, you get tension force minus 8 equals 2A. There's one equation. Good? All right. Now, second equation. Net torque equals net torque. We got to choose a pivot point here. There are two ways of doing it. The first time I did it, I was thinking it would be easier to choose this as a pivot point. It works, but you can't use the parallel axis theorem. I think I overthought it. I think it's easier to just pick the center as the pivot point, because then you don't need to worry about the torque from gravity. I don't know. It's up to you. Either way works. If you choose this as your pivot point, you don't need a system of equations. You just find your angular acceleration directly, and then use a jumper to find the linear acceleration. So I guess that's the advantage of doing it that way. All right, so anyway, let's continue along going this way. So our net torque, so that's I alpha, right? So I alpha equals the torque from the applied force minus the torque from the tension. These are both tension forces, so that's kind of weird terminology, but everybody good?
Yeah.
All right, so let's plug in our numbers. Let's see. I is mr squared, so 2 times 0.1 squared over 2, that's my I. Everybody good up to there?
Yep.
My alpha, I'm going to write that as A over R.
Yes, yes.
Follow? Equals the torque from A is 12 newtons times the radius minus the tension force times the radius. Simplify this mess and you get 0.1A, oh well, equals, look, on this side I've got 12 times 0.1 minus FT times 0.1, right? Don't all the 0.1s cancel? Ah, failed. That was a weird noise. All right, so let's see. These guys cancel, and then this, and this all cancel. So you end up with A equals 12 minus FT. So now I have a system of equations, and you can solve for both A and F of T, or FT, force of tension. Seven.
Can you scroll up to this purple on the top?
Yeah, let me do this. Sorry, give me 1 second. No. There we go. Sorry about that. There you go.
Alright, thank you.
Yep, my bad.
Oh, God.
So let's finish this, you guys. Thanks. All right, so this is a really good problem-solving strategy, you guys. Anytime you're looking for the acceleration of a thing that is moving and rolling, two equations. Net force equals net force, net torque equals net torque. Cool? Any problems? All right. Part B says calculate the angular speed of the disk after 3 seconds. Part C, oh, that's a terrible color. Part C, I want to know the angular speed after 3 seconds, right? Well, I just found my acceleration. Is it okay that everybody okay with solving this? I guess I can tell you the answers. So if you solve this, we're going to write it anywhere. Move on. So the acceleration turns out to be 1.3 meters a second squared, and the tension turns out to be 10.6 repeating newtons. That's because you used 9.8 instead of 10. Yeah, if you use 9.8, you get 1.47. And both answers are acceptable. It's surprising it makes that big of a difference.
Couldn't you write off the page?
Couldn't you what?
Write off the page if you want to.
Over here, no, it doesn't want to check. Wish it did.
That's annoying.
Yeah, I
I
know.
like
It's like,
Durango.
okay, everybody good? All right, so we just found our acceleration. It's 1.3 meters a second squared. We know our time is 3 seconds. We know our initial velocity is 0. Vf equals Vi plus At. So your final velocity is going to end up being 4 meters a second.
Wait, is that for C?
Yeah.
It says angular speed.
Yep, and then you can use
Oh,
a jumper
Sorry.
to find your angular
Can
velocity.
you use the jumper before to get angular acceleration and then just do it from there?
Absolutely, yeah. So yeah, there's a bunch of ways of getting at this one. And so you end up getting 40 radians per second. Cool? Part D, this one sucks. It's just tedious and annoying. It says the disk is replaced, oh no, sorry, I'm ahead of myself. Calculate the increase in total mechanical energy of the disk. So you gotta do it. You gotta slog through all the calculations. So as the disk moves up, what kinds of energy is it gaining? GPE, RKE, and KE, right? So here are the things we know.
I got it wrong entirely.
So we can find our final kinetic energy using 1/2 mv squared, right? Right? And we know that that final velocity, we just found it. It was 4 meters a second, right? So you guys agree we can find our final kinetic energy?
Yeah.
Cool. Rotational kinetic energy is 1/2 I omega squared. We know our I, we just found our omega, plug your numbers in. Do you guys agree we can find our RKE?
Yeah.
All right, the one that's kind of a pain is the GPE, because we got to figure out how far this thing moved up. All right, so there's a way to do it that's actually not terrible. So we got to figure out how far the thing moved up. So here are the things that I know. I know that the time is 3 seconds. I know the linear acceleration is 1.3 meters a second squared. I know the final velocity is 4 meters a second. I know the initial velocity is 0. That's all linear. I'm trying to find
Delta X.
how far it went up.
Delta X.
So find your delta x using any of the kinematics equations. 1/2 at squared, you can find average velocity times time. Average velocity is going to be 2 times 3, so 6 meters. Cool? And so now I can do my GPE is mgh, where 6 meters is my h. And then add up the 3 types of energy, KE, GPE, and RKE. Oh.
So for getting all the points on the FRQ, you said that you have to write out all the steps. So if you wrote all those tables out on the side, would that count as if you went from like the symbols to the equations and then like or would you say do it every step even if you've written out what you calculated?
I don't think you need to repeat yourself anywhere, if that's what you're asking.
Yes. Because like if you like, because some of these answers we found in like previous apart. So if you like rewrote all the stuff, like given stuff on the side.
That's
you
totally fine, yeah.
calculated, and then just plugged it in so you didn't like write it more than once. Or
Yeah,
whatever.
that's all. All right, everybody good with that? All right, and then finally, ooh, we finished this whole thing. Go us. E, the disk is replaced by a hoop with the same mass and radius. Indicate if the linear acceleration will be bigger, less, or the same. What do you got? Less, right? Because a hoop has.
Higher.
Okay, so if you don't remember, somebody defend for me. Why does a hoop have more rotational inertia if it has the same mass and radius? What do you got, Johnny?
Since mass is more concentrated on the outside.
More of the mass is farther away from your pivot point. Okay?
It's kind of, imagine like a point particle that's just traced all the way around. That's kind of like.
That's exactly what it is. That's exactly what it is.
Sir,
Yes.
so when they're like asking.
Hold on, you guys. We still got a couple minutes.
When they're asking for like justification, you just like, I just wrote like 4 to the I alpha, like, since the inertia is increasing, the angular acceleration would have to decrease to alpha.
Perfect. Yeah. Yeah, that one, the justification they had there was pretty small. They basically just said, since the mass and radius are the same, the hoop is going to have more inertia and therefore less acceleration, and they left it at that. But yeah, that's one of those things, like sometimes, be as detailed as you can without being ridiculously so, you know? All right, so here's the deal.
I mean,